resistance is more than 50% less than static CMOS and is closer to the NMOS circuits. We can say these are the block. This is called your pull-up network, pull-down network. So pull-down network can prepare the whole circuit. Okay, so that is why we have seen various examples also. So these are the advantages, that speed of operation will be high because we have removed all the PMOS circuits available in the conventional CMOS devices. Okay, so that will leads to a lower static power dissipations. Okay, and no short circuit power dissipations. Okay, no glitching of power dissipations. Okay, so since it is controlled by the clock, there is no path from VDD to ground at any point of time. Therefore, static power consumption is there. So what is the major cause of static power consumption? Is the direct path from VDD to ground. Okay, so that is why in this case we don't have direct path from VDD to ground. Why? Because we have used this particular transistor as a clock, and as you know that this will perform in two stages. One is called the pre-charging and second is called the evaluate phase. So we have seen certain diagrams also, like this is the diagram. Okay, and this pull-up network, and the dynamic logic beauty is that it can be prepared from both the network. It can be prepared from the pull-up network, or it can be made up from the pull-down network. So if it is made from the pull-down network, this is the circuit can be used, and if it is made up from the pull-up network, this is the circuit can be utilized. Okay, if we have only PMOS is used as a pull-up network, and here the NMOS is used. So these are the alternative where, as per the requirement, this dynamic circuits can be utilized for the applications. Okay, and we have also seen that apart from the advantages, there are some disadvantages. Okay, so what are those disadvantages of the dynamic circuits? So dynamic circuit disadvantage, first we have seen that there is a charge leakage problem. Okay, what is the charge leakage problem? Okay, so we discussed about the charge leakage problem, and charge leakage problem is coming from the diode, vertical diode that is prepared in the MOSFET structure. Okay, because this is N region and this is the P region, and we make a vertical diode, and it is more severe in case of when it is a more reverse bias. You know that the leakage current occurs in the reverse bias conditions. Okay, so as you know that this particular terminal is at the pre-charging phase, it is make it to VDD, so it can be connected to one of the terminals like drain terminal, so it will be make a VDD, so that will make a reverse bias of the diodes. So that will, if the reverse bias is obtained, so it will lead to a current in the range of 0.1 nanoampere to 0.9 nanoampere as per the device at room temperature. Okay, and this is the leakage current equation of a diode or reverse saturation current that you can easily identify from the diode equations. Okay, so this is one of the problem in case of a dynamic CMOS circuit. It is not happening in the CMOS circuit. Why? Because there is no concept of pre-charge, and this is coming because we are using pre-charging the output node to the VDD. So always our output will be equal to VDD unless there is a suitable operation has been performed to lower down the terminals. Is it clear to all of you? Is there any questions related with the charge leakage problem? So second point, disadvantage, we discussed charge leakage problem. There are three main disadvantages as I listed here. Second disadvantage is most important, charge sharing problem. Okay, so I'll go to the slide of charge sharing problem. So what is the charge sharing problem basically? So charge sharing problems is occur in case of a such kind of structure. This, if you can see, this is the dynamic logic circuit. Can anybody guess which kind of dynamic logic circuit it is? What is the function of this dynamic logic circuit by seeing from the diagram itself? So how many inputs will be there? There will be three inputs, right? A, B and A, B, C, right? So what will be this can be a which kind of circuit?
NAND.
Yeah, yes, 3 input NAND gate, right? Because these three things are in series, simple. And we have used a dynamic logic circuit. Here there will be clock, here there will be clock. If it is clock is 0, then both are complementary to each other. If it is 0, this it will become 1, right? So a pre-charging phase, in the pre-charging phase, what will happen? This should be equal to 0. So this will make the transistor on, and that it will charge to the VDD state. So initially the output will be, this capacitor will charge to fill the value that is equal to VDD, then output will be remain at the VDD. Okay. So what is the disadvantage here is that we are talking about the charge sharing problem. Okay, charge sharing problem. First, we already discussed about the leakage problem. What is the leakage problem? That is a device leakage problem. It is not charge leakage, device leakage problem, where these are the two methods can be used to remove the charge leakage problem. Right. So, but the main important thing is here charge sharing problem. This is a conceptual based. Please try to understand. Okay. So before switches are closed, the CL is given by the VDD. Okay. And the charges at the node B and C is equal to 0, right? So since if it is charged to VDD, what will happen? These transistors are maybe at the different positions, depend upon the inputs. It can be on or off, depend upon the input. Okay, so let's say what will happen if we consider the input is 1, 1 and 0. So if we input is 1, 1, 0, what will happen? This transistor is on, this transistor is on, but this transistor will be remain off. Okay, so if this particular node is charged to VDD, what will happen? And when we make a evaluate phase, once we make a evaluate phase, this clock will be equal to 1. So this become off. Okay, so in this particular input condition 1, 1, 0, what will happen? This is a capacitor node. Okay, our output node with this charged with some capacitance, so it will try to leakage. Okay, and because as you know that this is the, you can say the structure, this is the structure, equivalent structure can be built from this particular structure circuit. So this is equivalent circuit of a bigger network. So what will happen? This is the load condition, and these switches are there. Okay, and these switches are basically on or off depending upon the input. Okay, it is connected to A directly. So it is a node. Basically, this is considered to be A node. Okay, and this is considered to be B node, and this is considered to be C node. Okay, so same thing is shown here. A node is, this is the A node. Okay, same thing here. Okay, and the B node is only active when this particular transistor will on. Okay, and C node will be active when only this particular transistor will on. So that is why it is act as a switch here. It is shown as a switch. It can be off or on depending upon the input. Okay, so if we consider 1, 1, that means we are considering this switch is on. Okay, if it is like this, if it is switch on, what will happen? The load capacitance is having the voltage equal to VDD, and there will be parallel arrangement like C1 and C2. Okay, so will be there. So after some time, what will happen is the voltage across VDD will remain same. I am asking a question that
No, sir.
yeah. So it will change, right? It will change. So, now question is in what proportion it is going to change? It is a simple problem of 3 capacitances connected in parallel. Okay, one capacitance is charged to VDD, and after that the circuit is connected. It's like, you can say, simple network problem. Okay, so what will happen after the sometimes happen like after the switch is closed, S1 and S2 switch are closed, what will be the voltage across the node A? Can anyone answer? What will be the node voltage across node A?
So the charge will get distributed in between the all the capacitors so that they all remain at the same potential.
Yeah. So the charge will be distributed. We know that all those things. I am directly asking about what will be the final voltage, because it is in parallel configuration. The voltage will remain same. Yes. Yes or no? And we know that in
Yes,
parallel
sir.
voltage won't change. Okay, so that is why just those are listening. This is very simple problem. We can say the overall charge that we have, that is Q CV is charge, CL into VDD is the charge. Okay, before activation of S1 and S2. So once it is activated S1 and S2, this charge will be can be replaced by this particular, because the capacitance has been changed. Three capacitance will be changed. So if the capacitance is changed, then voltage will also change, right? Because the total charge will remain same. Getting or not? Okay. So you can say this is before switch close and this is after switch close. Okay. Then we can say that what is the equivalent voltage can be find out, very simple expression by using this expression, CL into VDD divided by total capacitance including C1 and C2. Right. So this way we can get the this particular VDD will be down by some X voltage. You can say Vx voltage. So that can be considered as a VA voltage. Now instead of VDD, it will be the VA voltage. Okay, that is considered. So this problem is called the charge sharing problem. So whatever charge present here will be shared by this. Okay, and if it is remain for a longer duration of time, what will happen? So the amount VA will going to down. Okay, and it will continuously goes down. If we take time, some 1 day, 2 day, and up to and so on, what will happen? It may occur that it will if the value of C1 and C2 is more, okay, and they are contributing towards getting more charge, what will happen? It will not remain up to VDD. It can go up to level 0, or if it is cross the noise margin portion, that that value will be go down and it can be disrupted. Yes. So that is why this problem is called the charge sharing problem. Okay, and this charge sharing problem is applicable only for a certain input conditions, not for the all input condition. Let's say if the input is 0 0 0, will the charge sharing problem will arise?
No, sir.
Yeah, right. So it will arise at what condition? Can you say at what different input condition the charge sharing problem will arise? Can we conclude? Any idea? I have just given example of a 110, right? Where the all the two capacitors are connected in feature. Will the charge sharing problem will arise at the input 111?
Yes, sir.
No.
No, sir, it will be grounded.
Yes, correct. Because your data will be changed, na? Output will be changed to 0 because it is the actual operation happening there, right? So that is why the worst scenario. This is called the worst scenario of the charge sharing. That worst scenario is that when the input is 110, right, and it can occur at 1 and 0 also, 100 also, right or not? So charge sharing will happen only between the CL and C1, right, in the two cases. And if it is we have seen 110, it will be like this: CL parallel with C1 C2, and 100 CL parallel with C1. And if it is still 0, so there is now a sharing problem because this transistor has become off. Okay, because there is no path to discharge this capacitance. Okay, so you can say in certain input conditions the charge sharing problem will arise, and that will leads to a problem when it is maintained at that particular input level for longer duration of time. Okay, and that will cause the flipping of information also. So that should not happen, flipping of information. That is you can become undesired phenomena. Okay, that we don't want. Okay, so during the evaluation phase, all the capacitors will discharge output to 0. That is the operation, right? When what is the meaning of evaluation phase? Evaluation phase means input is, let's say, 111. See, in all the cases, all the capacitance will be discharged to ground. This whatever capacitance will be there here, all the cases it will be equal to ground. Okay, so this is the dynamic circuit charge sharing problem. Okay, so solution. What is the solution? Can be a charge sharing problem. What can be a solution to charge sharing problem? Is that you know that that CL into VDD is equal to this much. We calculated the value of the VA. Okay, so let's assume that C1 and C2 equal to 0.5 into CL, approximately 50% of the load. So what will happen? VA will be equal to how much? VDD by 2. Is it correct or not? Okay, so it will be equal to VDD by 2. So after redistribution of the charge, output is VDD by 2, but ideally it should be VDD. Yes or no? Yes. So the output may be treated as low. So it cannot be treated as logic 1 always. VDD is treated as logic 1, so VDD by 2 maybe I'm not sure. It depends on what is the noise margin level. Okay, so if output is VDD by 2, so that is a problem. Okay, so that is why we want to correct it. So what is the method of correction? Is that method of correction you can see in the diagram. So if it is a n block making of a dynamic logic, so what we need to do, we need to put one PMOS extra in parallel with this particular clock. So this one PMOS, and that should be grounded just like a pseudo NMOS circuitry. You might be aware about the pseudo NMOS logic, right? So pseudo NMOS logic may one PMOS that is connected to ground. So what will happen? Whatever the charge leakage will happen at certain input condition, and this is the PMOS is connected to ground. That means some portion of the current is coming from here always. Okay, I reference a current. Some current will be coming. Okay, and it is a weak PMOS. So weak PMOS, that means the resistance value will be high, very high resistance value. So if very high resistance value, the current flowing here will be low. I will be very low. So we will providing very small amount of current to this particular node, so that it will the charge at this particular node will be always at the VDD. It should not go down like VDD by 2 as in case of a charge sharing. Are getting the point? The solution. So I'll read it. Weak PMOS, small W bar is added as a pull-up transistor. In the transistor always remain on and behave like a pseudo NMOS circuit during the evaluation phase. Okay, although there is a static power dissipation due to this during the evaluation phase, it helps to maintain the voltage by the charge loss due to leakage current and charge sharing problem. Okay, so the why this charge sharing and charge leakage problem is arises because of we are charging the output voltage to VDD. Okay, and after the evaluation phase, it may not to lead to a VDD value, so that may degrade it. So for that we are introducing one PMOS so that it will restore its previous value. So by adding the inverter with PMOS will return off the PMOS during the evaluation phase. So weak PMOS always not fight with the NMOS block. Apart from this, static power dissipation issue can also be overcome by the inverter. So another thing is that, right? So this will leak. The correct way of doing is that utilize this circuit. Okay, so whatever if anything is there, like if it is a VDD, what will happen? With this VDD is connected to zero node, and this zero node is, that means it is always on. Okay, so instead of a grounding here, so we can do another exercise. By adding an inverter with the PMOS, will turn off the weak PMOS during the evaluation phase. When the evaluation phase will happen, this will make a ground, because in this case, when the evaluation phase is happening, this will be always VDD. Okay, that should not be a practice, right? So during the evaluation phase, what will happen when this particular is grounded? So if it is grounded to 0, this will be equal to VDD. If it will become the VDD, this transistor will remain off. Okay, are you getting the point? Are you getting the difference between the two circuits? Okay, so during the evaluate phase, also we can reduce the static power dissipation by adding some inverter in this at the output node of the dynamic logic circuit. So this is the correction we need to do. Okay, for maintaining a good dynamic CMOS. Okay, with minimum leakage current, right? So this is the addition we can do. So we'll opt for this particular circuit if we are designing for any n number of circuits or any digital integrated circuit compared to this circuit. Okay, because this circuit still have the leakage power dissipation during the evaluation phase. is similar in case of, you can correlate with the pseudo NMOS logic if you have studied, right? So third problem is called the charge dynamic CMOS problem, that is called the skew problem, charge skew problem. Okay, so that skew problem is also related with the timing diagrams and all. Okay, and timing diagrams and all we'll discuss during the timing diagram will discuss in the sequential circuit when you go into dual the sequential circuit. So let us first understand what is skew mean. Skew is that when two or both the clocks are not coming simultaneously. Like if it is a 5-1 clock, okay, and if the next block is connected, because one dynamic logic has to drive the another network, it is not the next stage. So you can say this is stage I and this is stage I plus 1. Okay, and even a sequential logic circuits, basically all the clock should be arrived simultaneously, right? Okay, but because of the path delay, or metal lines are connected to, suppose one is sitting at this particular location transistor and another at this particular location, and VDD is near to this, clock is near to this. So what will happen? So here the clock will come early, and because of the big networks of the path, clock will arrive late here. Okay, so this problem is called the clock skew problem. Okay, clock skew. Clock is delayed by delayed in other parallel configurations. Suppose maybe same block is repeated here. This is ith block, and this is I plus 1 block. Same block is repeated here also. So what we synchronous applications, it's not coming simultaneously. Then that is called the clock. Logic. So and nothing but logic as well as the dominant logic. So dominant with dynamic. Okay. Is the combinations. Okay. Right. And second component is the CMOS inverter. Suppose you so this is fact. So the advantage using the dynamic logic we have getting F bar here. Okay, so if it is, it will be F bar, right? So it is a reduced chip area. Okay, if you use in this fashion, okay, high speed of operation because you are using dynamic logic, no short circuit power. So all the advantages of the dynamic will be combined here as a domino logic circuit, you can say. So another thing is limitation. So each gate required an inverting buffer. That is the limitation. Inverting for every stage there should be some inverter is there. All the gates are non-inverting in nature. Okay, all the gates are non-inverting in nature. So always will not get the useful things in terms of if we are making like domino logic, so that will give a non-inverting kind of thing because we have kept one static inverter only. So only thing that we need to remember that the name only. So domino means that is combination of a dynamic CMOS as well as the static inverter. Okay, that's it. There is only, you can say, the purpose is just to invert the logic. That's it. So these are the some domino CMOS circuit, how it can be utilized, right? So how to deal with non-inverting property of the domino logic. So recurrence logic using bubble shifting to transform the circuit. It is called dual rail domino logic. Okay. So these things all are there in the your book. You can go through and about this. It's not very tough. Okay. The important thing that I'm going to discuss here, that is called the one more logic, that is called the NORA logic. NORA stands for no race condition. Okay. So you might be aware about the race around condition. Okay, what is race around condition is that, so when we have a, what is the problem with the dynamic logic, right? So problem with the dynamic logic, that if it is a one n block and it is always connected to VDD, okay, and if we have, let's say again we have an n block, what will happen? So since n, it is an n block, it will be connected to one of the NMOS. So what will happen if it is VDD and it is connected to NMOS? What will happen? One input is directly coming to this particular n block, and it will remain on always. Okay, that should not happen. Okay, that should not happen. So what will happen? This will be pre-charged to VDD, and then charge sharing problem will always be arising in the second stage. I'm talking about the second stage, not in the first stage. Okay, so that is the major disadvantage. Okay, if we are using n block and repetitively with the n block, okay, so what is the solution for that? Solution is that either you go for a domino logic, right? You put inverter after this particular point, you put inverter, and then you replicate it. So that is why it is named as different. So all the domino logics can be connected in series, domino 1, domino 2, domino 3, right? So this is the one method of realizing the circuit. And second is the alternative one called the NORA logic. Okay, if you don't want to use the inverter repetitively, what we need to do? You just use the n block and p block concept. And what is the n block and p block concept? As we know that in the dynamic logic, n block is prepared equivalent to p block, or p block can be prepared equivalent to n block, okay, by using the pull up network or pull down network only, right? So in this case you can see that what if it is pre-charged, so always it will be equal to VDD, and if it is VDD goes to the PMOS block, what will happen? If it is connected to one of the PMOS, it is a high logic, that means it is connected to this point, so this transistor will not be get affected, it will be remain off, right? It will not get affected. Okay, it will be get affected only when we will change the input conditions and all, right? So that is why this particular logic is called the no race condition. In the previous thing, right, when NMOS block is directly connected to this particular network and that NMOS is continuously working, that will arise a problem. Okay, that will flip the information in the subsequent stages. Okay. So in this NORA logic, there will be no such cases. That is why it is called the no race logic or NORA logic, or you can say it is a combination of a dynamic logic having n block and p block together. So this will be, you can say this is the first stage, and this will consider as the second stage, and this is again third stage. So you can say you can make number of integrated circuit using the dynamic logic by odd number of things putting n blocks, like, so it is a stage 1 and 3, so odd number of, after n block will be get repeated in the odd number and the p block will get repeated in the even number. Okay, so this way you can prepare the whole complete logic circuit. Okay, I'll give some example. Okay, and benefit also. So this is the one technique. So here what will happen, both the NMOS and p blocks are in pre-charge phase when clock is high. Okay, because you can see this is clock and this is clock bar. Okay, so by this NORA logic approach, we can avoid clock skew problem. Okay, so compared to the domino logic technique, this approach is give higher flexibility as we are using p block also instead of only n block. So that is why it is giving more flexibility. So both the inverted and non-inverted signals are available in the NORA logic. As you can say, this is the implemented block, and p block will have another implemented block. Okay, so you can say what was prepared using NORA logic is that DC alpha processor. That is the 250 megahertz CMOS microprocessor that extensive use of neurologic circuit. Okay, that has been utilized for making the product. So this is one example of a how to realize the bigger network using the domino logic or NORA logic. Okay, so I am just giving a full adder example of a full adder circuit. Okay. So what kind of full adder circuit you are going to design? The full adder circuit, you might be aware what is the equation of full adder circuits. This is the simple. There will be three inputs. The input A, B, and the third input will be the carry, right? And this will be a carry in, and this is sum and carry out. So I think you are aware of this full adder network, right? So only thing is that you need you might have when made the full adder using the logic gates, okay? But here you need to prepare the full adder circuit using the transistors. Are you getting the point? Okay, and there is a question I am talking about in terms of question paper. Okay, the question is that realize the full adder circuit using the domino logic and NORA logic. The domino CMOS logic and NORA logic. Or simple, you can say that you realize the circuit using the conventional CMOS also. Okay, we can have a conventional CMOS also instead of a domino logic. We can have a conventional CMOS logic, static logic. We can make a I think this is the full adder using the static logic. Okay, static, because it is no clock is mentioned here. You can see that. So this is the complete. How many transistors are required? You can see how many transistors are required. The huge number of transistors are required, right, for making a one full adder only. So you can see the beauty of integrated circuits. There are billions of number of transistors in one chip, because there are not only one full adder, there will be millions kind of arithmetic and logic unit, right, for making the full processor. So how we can understand the circuit basically? So simple, we have to go to the equations. What is the output? This is the sum and carry. These two things are required. So you go to the Boolean expression, and you know that if you know the Boolean expression, then we can make a simple. Then we can make, they can make any kind of circuits, right? If you know the Boolean expression. So find out the Boolean expression of the full adder. So this is the Boolean expression of the full adder, right? What is AB plus BC plus CA? Right. Sorry, that is the carry, right? Okay. Sum is having 4 components. There will be some. You can realize using K-map. If you have studied the K-map, you can realize all this using the truth table and all. Okay, what will the sum equation? So I'm just directly writing the sum for in terms of time. I'm directly writing the equations. Okay, so C naught is nothing but AB plus BC plus CA, nothing else. Okay, okay, AB plus C in A plus B, that you can say is nothing but AB plus AC plus BC. Simple product of 3 different inputs. Okay, so how to realize that? How to realize that? Okay, we can make it by easy way. Okay, so before that, we will focus on the sum. So realized first. This is A, B, the carry. Okay, so AB plus, if and then we have no the logic. This will make pull down C and combine network, pull up together network, pull up network, right? So if A and B in parallel and A and B in series, that means parallel, that will make A and B in series, and then C is in series, that will make C in parallel. So that will make C bar. We are getting the output C bar, not C. Remember this, okay? By using the conventional static logic. So that is why we required an inverter. So we kept one inverter here, right? Kept one inverter. What is the input here going? The input is C bar, C dot, C output. Okay. So because why it has been done like this way? Because in this equation you can see the whatever sum will have this particular thing in the equations. Okay, there will be this will be used as a in the calculations. Okay, while during the sum, because if you write in the detailed form of sum, it will be make a complicated circuit. If you do the minimization first, that is the rule of minimization. If you do the minimization of Boolean expression, then the result of the circuits that is relies from the minimized structure will be minimum, right? So now you can see the second stage, A, B, and C. There are three input. You can say this is 3-input NAND gate. So just see this A, B, C in parallel here, and A, B, C in series here, right? Right, and you can consider this is X plus Y, simple way. And what is Y is being built upon, and Y depends on A, B, and C in. So you can see this, it depends on A, B, and C in as well as C out, So this one. Okay, so that is why you can say this is X and this is Y. Okay, X plus Y. So that is both. That is why both are in parallel. And here also this is X and Y. So both are in series. So this will make the complete network that will make the output as a S bar, because always we'll get a complementary network. So if we'll get a S bar, to get the S, what we required a CMOS inverter. And then we always get a C bar. So to make a C output to correlate with this, we'll get the C out. Okay. So hope you have understood the full adder circuit, right? This is one way of realizing the full adder circuit using the equations, Boolean expressions. Okay, that is the important of Boolean expression. So you know that all those things, how to make a circuit using the Boolean expression. Same thing has been done here for making realization of a complete module that is called the full adder circuit. Okay, so next question is that if we want to realize the same thing using the logic that is called the NORA logic, we have studied. Okay, so NORA logic, for that this is the circuit diagram, right? That will make some simple is compared. You can see count number of transistors. So here I think maybe 24 or 26 number of transistors are used. Okay, I'm not able to count the exact number. 24 transistors are being used. So if we are realizing the same full adder network using the dynamic logic that is called the NORA logic, right? We have the clock here, clock bar. This is the clock. I can say this is the N block logic, N block, and this is called the P block, right? So P block, I am just correlating. I am making this kind of circuit, right? I am just making the full adder using these two blocks, first and second stage. Okay, first stage will be based on the NMOS network, and second stage will be based on the PMOS network. So exactly this will be there, and output of this will be claimed as a sum or carry. So just see this network. Okay, so this is an N block. So N block will consist of the information clock, and clock will be there, right? Always there. And we have A, B, and A, B, C. These things we need to require. So we required what? We required only pull down number transistors. So whatever pull down network I have there, I'll just copy here. Whatever pull down network here, that I'll just copy here. We have AB in series and AB parallel and C in. Just see here, AB in series and AB in parallel and C in. So that will give the C out network. So the P network has been redundant. So it will give my output as a C bar, right? and then if you want to take it out, then you can directly go to Cout. So this will be equal to carry out for a full headed network, right? So as you know that in the equation that carry out bar has been used in the sum network. Okay, so that is why we need a particular Cout bar to be act as a input. And as you know that this is always pre-charged to VDD. That is why we are going towards N blocks to P block. This is a P block. From here onwards, we have a P block. So P block will have how many number of inputs? We need to see from the expressions. So we required A, B, C in and Cout. These are the 4 inputs we require. So this is the Cout we have. Input is the Cout, and another 3 inputs are, these are the 3 inputs in product form. The first one, okay, and then in parallel with that means we have realized this particular logic, ABC in and Cout. This we have realized, and then again ABC in should be realized, and then should be in plus. That plus means in the P network, what is the meaning of plus? That they should be in series. So this ABC will be there in parallel. So that will make A plus B plus C. Sorry, that will make ABC, right? This will make ABC in, and this will make A plus B plus C in, right? This will make A plus, then in the yeah, and then it will make C dot like this here. So I will get the output as this particular logic is a S bar. Okay, so we'll get a S bar here, and if you want to realize S from here, so it will become like this. So by using the NORA logic, we can save number of transistors. So how many transistor number can be saved? You can count here: 2, 5, 6, 7, 8. So here only 19 number of transistors are being used. Okay, 19T. But here in the earlier static network, what we can see, it was more than that, around 24 number of transistors used. So we can reduce the number of transistors count. So if you reduce the number of transistor count, what will happen? You know that it will be a faster design compared to the conventional CMOS logic. So this way you can analyze n number of network and n number of combinational logics. Any combinational logic you can basically use and utilize by using the domino logic or NORA logic or dynamic logic or static logic. Okay, so is there any questions? I'm going to end here my presentation. In the next class we'll start with the sequential logic circuits, okay, and then memory. So these 2 topics are remaining, and this all these things are come under combinational logic circuit. How you can say combinational CMOS circuit. So you can refer the book, Neil West book is there, okay, and there you can find out the details of the circuits. So any questions from the students? Please read the things in the book. Okay, I'll also share the slide about the dynamic logic as well as whatever the things we have discussed today. Okay, this was the very important concept. Okay, it will help you to write answer in the question paper, as well as it will help to realize any kind of circuit if you are making a projects from this. If you are working in project in the VLSI design, so this kind of circuit you might be aware. You should get aware and utilize for useful applications for making the integrated circuits. So because the logics are very important, and because of the logics only we can design the circuits. So go for a logic, okay, apply some logic on the logic gates or logic circuits. Okay, don't just see this is the complicated networks and all. No, so just nothing but they are a combination of the series and parallel. Okay, so you have to understand how the things can be realized using the different logic circuit like dynamic logic circuit or static logic circuit. We have a given example of a full adder circuit using the static CMOS as well as the NORA logic. You can see the difference, how they can be prepared. Okay, so get acquainted with that. Okay, and as I told, next week we are going to conduct one quiz for the all the student online quiz for the remaining portion of the midterm examinations. So I'll take I think two or three lectures to complete the remaining part. As I told, two topics are remaining. One is about the sequential logic circuits, and the one is related to the memory. Okay. So is there any questions from the students? So you can make please a note of attendance. If you attending online, please mark your attendance here. I have just opened the response sheet. You can please mark your attendance and then you can leave.
Thank you, sir.
Yes. Okay.